All right, so let's continue on circuits. We're looking at in series and parallel. And so when we're talking about um, elements in series, we're looking at something like this, where they're lined up, so they just fall in a line. And so this would be in series. And then when they're on opposite lines, like this, so we draw it out, and that's obviously parallel. And so what we're going to do is we're just going to basically just get some rules of how we can start analyzing these circuits. And the idea is that we're going to take these and we're going to create some equivalent resistance when we have resistors. So the first thing we'll look at is going to be in series. So in series, what we want to do is we want to use Kirchhoff's in series. I can't spell today. Anyway, yeah, no, that's right. It just looks weird for me. I think I've been writing it a lot, so it seems weird. Anyway, in series. So the idea is Kirchhoff's laws. So we have electromotive force or EMF, and then it comes around and it passes through a negative IR, and then it goes through another negative IR, and then it comes back. And if we sum these up, Kirchhoff says that the EMF minus IR1 minus IR2 is equal to 0. This is what we did last section. So what we want to do is we're going to solve this for I. So why don't we move these, since they're negatives, we're going to move them to the other side. So the EMF is going to be IR1 plus IR2. And then we can factor out this I. So the EMF is going to be I times R1 plus R2 and so I is going to be EMF over R1 plus R2. And so the basic idea is that we can see that we could create an equivalent resistance which is going to be equal to R1 plus R2. So the current that goes across both of these is going to be the same, and the potential difference then is going to be reduced. It's shared by both of these, and it's just divided by however many there are, or rather by the resistance across both of these. And so we write it like this, and on your equation sheet it has that R in series is equal to, R1 plus R2 plus however many plus R to the I. However many resistances you have, you add them up, and that creates your equivalent resistance. So R in series is the sum of all of the resistances. That's resistance in series. The thing to remember with in series is that the current is the same across both of these. So the current is the same. However, the EMF is shared across both of them. So if I had a 9-volt battery, that would be split across both of these. So this would be 4.5 and 4.5. So we have a reduction. If I added another resistance, well, then this would all just be divided by the 3. And so that would be my potential difference if they were equivalent resistors. That's the idea. So for example, let's talk about Christmas lights. 'Tis the season. So suppose you had some Christmas lights. They were connected to a 120 volt source, and along this you had 50. I'm not going to draw them, but you had 50 bulbs. 50. All right. So we got 50 of these things. How many? What's the potential difference? So what's the potential difference on each bulb? And so we could do that pretty simply. So the electromotive force using Kirchhoff's minus the potential difference of 1 minus the potential difference of 2 and so on, minus minus the potential difference of 50. That has to be equal to 0. And then we can rearrange that. So the electromotive force is going to be the potential difference of 1. I keep doing that. plus potential difference of 2 all the way up to the potential difference of 50. So what we have is that the electromotive force is going to be 50 times the potential difference. So the potential difference on one of them, that's because they're all the same. They're all the same type of bulb. So the potential difference is going to be the EMF divided by 50. And in this case, it would be 120 divided by 50, which would give me a potential difference of 2.4 volts on each bulb. So the potential difference gets shared across it. Yeah, it's pretty simple. You just add them up. It's not a big deal. It's in the parallel. That's where things get a little tricky. So let me get a new page open. All right. So now we're talking in parallel. So in parallel again, just to draw it. So we have a resistor. My drawing's all off. Whatever. You get it. All right, so we have R1 and R2. And now we have to think about the current because we have a junction. So we know that the current by Kirchhoff's junction rule is going to split. We're going to have some current out of the battery over here. And then it's going to split into, we'll say I1 and I2. And then it gets back together, and when it comes back, we're back to the original current coming back in. And so just, you can think about it like water, you know, it's going to come in and then it's going to split off. So we're going to have less current across these two. But we know that the current of the battery, out of the battery, is going to be equal to the current across resistor 1 plus the current across resistor 2. And then using our definition, current is the potential difference divided by resistance, we can substitute. So we'll substitute this in for each of these. So the current across the battery is going to be delta V over R1 plus delta V over R2, where the potential difference is whatever's created by the battery. That's our EMF. But I'm going to leave it as delta V. So we'll factor that out, and we get IB. The current is going to be delta V times 1 over R1 plus 1 over R2. And the idea is that we can shrink these down into equivalent resistances. And so if we did that, we would basically have like one resistor. And this is an equivalent resistor. And so the equivalent resistor is right here. And this is like what we did with series. So we can combine them together. However, this one, the only thing that makes it tricky is you have this 1 over R parallel. And that's going to be equal to 1 over R1 plus 1 over R2 plus dot 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 plus 1 over Ri. And so on your equation sheet it looks like this. 1 over resistor parallel is equal to the sum of 1 over the resistors I. So the only trick with this is that we add them up, but then we have to always invert it. So it's always 1 over the sum, and that would be our resistance. But that's it. That's series and parallel.